Now in this lecture we shall be understanding that how or the what are the guidelines that the AS1170 part 2 is giving to help us calculate the internal pressure coefficients, that is the value of the CPI as per different we can say cases. Now the broadly the first case or the first classification is dependent upon the we can say the opening area, that is the opening area. So if that opening area is we can say less than 0.5%, for that we do need to refer to the table 5.1a. If that opening area is greater than we can say 0.5%, for that we do need to refer to the table 5.1b. Now that is the the thing that we or these are the tables that we are going to discuss in detail in this particular lecture. But before that, let me just show you 2 to 3 pictures. Just as a basic engineering, we can say calculations. If you're assigned a task that you do need to find out the internal pressure coefficients for these two type of building. First is this particular building, which we can say is effectively there's nothing except doors and windows in this particular we can say arrangement. But in this particular case, the it is a combination. Like we have windows also, we have this door also, and we have a brick wall also. So as an common engineering judgment, we can say that internal pressure coefficient shall be different for this case and this case. That is the first concept. Now second concept is that what exactly or how exactly the code is guiding us, that how we can calculate that. Now in addition to the CPI value being dependent upon the opening area. Now if we are talking about the opening area, we are talking about a ratio also. First is the opening area that we have understood. Second is the ratio. So if we refer to the table here, let me just show you a table. So in this table you can see that basically this ratio is given 0.5 or less, 1, 2, 3, 6 or more. So in here, what exactly is this ratio? This ratio is basically the area of openings on one surface to the sum of total open area, including permeability of other walls and roof surfaces. Let me just write it down again. The ratio is equal to area of openings on one surface divided by sum of total open area including permeability of other walls and roof surfaces. Now in here, I just want to, highlight the term. We're talking about the other. In here, we're talking about one surface. So area of opening on one surface to the sum of total open area, but on the other walls and roof surfaces. So if you're selecting one wall here, we are not taking that calculation in here also. So let us say, this particular number here. Let us say this particular number here is 2. And this particular number here is, we can say 3. So the value or the ratio that comes out to be 2/3. That is approximately, we can say 0.67. So that is how, we can do this calculation. So broadly, we are getting the, we can say some basic understanding here. That first of all, we're talking about the opening area. Opening area is different, ratio is different. Opening area is basically, we can say the percentage, or we can say the total opening area correspond to either less than 0.5% or greater than 0.5%. Second thing is the ratio of the area of opening on one surface to the total open area. So we already discussed in detail in the earlier lecture that how we can calculate the opening area. So that is the, these are the two terms, and we shall discuss in much more detail very shortly. But opening area and the ratio. Now the third concept that we do need to understand before we proceed further with detailing detailed understanding of table 5.1a and 5.1b is that what exactly shall be the case where 5.1a shall be applicable, and where exactly shall be the case where table 5.1b shall be applicable. So for that, the clause that is being referred is basically 5.3.1.2, and for table 5.1b the clause is 5.3.1.3. Now if we refer to the table 5.3.1.2, it is basically applicable, this table that is applicable, we can say, for all cases having, we can say, opening greater than, without having opening greater than 0.5%, or we can say less than 0.5% of the wall area, and the roof should be impermeable. Now this case, it can be, we can say, in region A0 to A5, B1 to B2, NZ1 to NZ4, and we can say again the case that we have discussed in the earlier lecture, that is in region C and D for the height greater than 25 meter. So we are not talking about the height less than 25 meter, we are talking about the height greater than 25 meter. So in region C and D, basically this is valid for above. But at the same time, the important condition is that in all of these cases, the roof should be impermeable and the walls should have an opening less than 0.5%. Only then we are dealing with this table 5.1a. Otherwise we have simply have to go suggest to the refer to table 5.1b. and as per my experience, this is the most common case that we have to use in practical structures. Second thing that we the next thing that we do need to understand here is that we are talking about the permeability. Now the condition here is that if one wall is permeable, now you can see here that there are some dotted line also, and there are some solid lines also. So this is the solid line and this is the dotted line. Now solid line, that is basically an impermeable surface, impermeable, and dotted line, that is basically permeable. So in here we can see that if this arrow is pointing towards it, that is the windward wall here, that is permeable, that is this particular case. So for that we do need to refer to the CPE for the windward wall. CPE, that we shall discuss in detail in the separate lecture, but that is an external pressure coefficient. And CPE for, we can say, windward wall, that can be referred to the table 5.2a. Table 5.2a of the same this particular code itself. And where if windward wall is impermeable, then we can simply refer to the CPIS minus 0.3. So in here you can see that the solid wall is getting exposed to the wind. So the windward wall here is impermeable. So that is why we can refer to the windward, the CPI value is minus 0.3. Now you can see here that we are talking about the minus value also, and we are talking about the plus values also. So if two values are shown, these are provided as a separate load cases. Now as a simple, the most important thing that we do need to understand for, we can say, engineering wind load calculations is that positive always act towards the structure and negative always acts away from the structure. So let us say this is the steel factory where steel building on which we are talking about the internal pressure coefficient. So if on one face the pressure is negative, it means that it is acting away from the building. And if on the second case, let us say it is positive, it means that pressure is acting towards the structure. In our case, we are talking about the CPI value. So if CPI internal pressure is minus 0.1, so if the value inside, that is basically negative, we can say. So it means that the pressure is acting away. And if in this case it is plus 0.2, it is positive. So it means that the external wind is putting pressure onto the building, and inside, or we can say there is this pressure. So that is the basic concept. So positive, we can say that is basically the pressure, and negative in this case, that is basically the suction. Now, in this particular case where 2 or 3 walls are permeable and other walls are impermeable, obviously because of lot of permeability is involved, so we can refer to a case where it is either pressure or it is either suction. It is either the internal pressure is positive or either in the internal pressure is negative. But at the same time, when the windward wall is impermeable, so in that particular case, it is negative. That is, we can say that suction shall only happen. After that, when all walls are impermeable, so in this particular case, when all walls are impermeable, the CPI is minus 0.3, and there shall not be any, we can say, positive value, but we have to refer to the zero value also, because in many cases it may happen that effective, we can say, contribution of CPI and CPE that may govern with zero also CPI. After that, a building effectively sealed and having non-opening window, that is very rare, I must say. And in my many years of experience, I have not encountered this kind of building. Then it may be for defense buildings, or it may be for a building where we are storing very secret information. But that is not a, we can say, a practical building where there is no opening in the windows and the roof is also impermeable. So that is not a, we can say, a regular building. So in that particular case, CPI value shall be minus 0.2 or 0. So whichever is most severe for the combined actions. Now this table 5.1a, that is valid when we can say the roof, when the roof is impermeable and the opening is less than 0.5%, it is without having opening greater than 0.5% of the wall area. So for that we do need to refer table 5.1a. Now understanding in detail about a table 5.1b, that is internal pressure coefficient CPI with opening greater than 0.5% of the area of the corresponding wall or roof. Here we are not talking about the permeability of the roof. We know that the roof is permeable, unlike in table 5.1a where the roof was also impermeable. Now second thing that we do need to understand here is that in here the values are not that simple. The values are not only the number, but there are these, we can say, equations also that we do need to solve. The equation typically for for these cells, that is basically, we can say, Ka, Kl and CPE. Now in the earlier lecture we have I have said verbally that CPI is basically a function of CPE also. That is not only, we can say, it is dependent upon the openings, and it not dependent upon the, we can say, permeability also. It is also dependent upon the external pressure also. So that is why in here we can say that CPE is also we can say written in the equations. But for the areas where there are large number of openings, that is this ratio, the ratio that we have discussed a few minutes back, that is openings of one surface to the sum of total open area. If this is in value of 2, 3 or 6 or more, in that particular case, it is basically, we can say, a function of Ka into Kl into CPE, where Ka is basically area reduction factor, L is the local pressure factor, and CPE is basically the external pressure coefficient that we shall discuss in detail in the next lecture, that how we can calculate the value of the CPE for different windward walls, leeward walls, side wall, upwind slope, downwind slope, crosswind slope. So all of these factors are we shall discuss in great detail. But in this lecture you need to understand that when we talk, this is the as per my experience, this shall be the table that we shall mostly be dealing with when we are designing the structures. And second thing, that if the ratio of the area is 0.5 or less, then more or less we are talking about this particular number itself, that is minus 0.3 or 0, that is given here. It is minus 0.3 or 0. Now in the second case, when we are having an opening area of 1, in that particular case we are talking about minus 0.1 and 0.2, that is this particular case. But if the largest opening is on the windward wall, it means that it is not like that we have to calculate the different values for all the sides. This table means that if your ratio of area of openings on all this ratio, that is let us say equal to 1, and I am saying and If largest opening is on the windward wall, then your CPI value shall be minus 0.1 and plus 0.2. But I am saying but here. But if the largest opening is on the side wall, then we do need to refer to this particular table. We do need to discard this. That is, if your ratio, if your ratio here we can say is 1, and if the largest opening, let us suppose, is on the leeward wall, then we do need to refer to minus 0.3 and 0. We do need to discard these values. So this is how we do need to find out the value of the CPI. Similarly, if the ratio is, let us say, 6 or more, then, and if the largest opening is on the leeward wall, then again we can refer to the Ka into KL into Cp. But again, you can simply see here that all of these values are same when the ratio is very high. So here also, if the largest opening is on the windward wall, then only it is reduced and multiplied with 0.85. But otherwise, in here, all of these values are same. That is Ka into KL into Cp. So that is the we can say basic understanding of the different tables that are given in the code. So I hope the table 5.1a and 5.1b is clear to you, that how we can calculate that. But additionally, you do need to understand some we can say one more point here, that we have simply understood here that table 5.1a is valid for all of these zones except for less than 25 meter in we can say zone C and D. So in here, for this particular area, even if our we can say opening is less than 0.5% and the roof is impermeable, then also for this particular area we do need to refer to this particular table, that is table 5.1b. But again, at the same time, if the we can say opening area is greater than 0.5% and we are talking about the permeable roof, then it does not depend, it is valid also for all the regions. But at the same time, we can say that only if this condition is met, we can refer to the table 5.1b, and this table also needs to be referred if these conditions are met, but at the same time we are talking about the region C and D, then in this particular area up to height less than 25 meters, 5.1b has to be applied. Now additionally, I just want to explain to you about the internal walls and ceilings also. We shall discuss in detail about the KV factor also, but before that, I just want to show you a diagram of one building. Let us say this is one building that you have designed, and in here they have installed we can say false ceiling like this, and there are these various we can say internal partition walls. This is the external wall, and let us say this is the internal wall, and there is this one more internal wall, and let us say there is this one more external we can say a wall that is just next to the external wall. Okay, so the wall just next to the external wall are labeled as orange, and the internal walls that are labeled as yellow. Now the first thing that, in mind that we do need to that we may face when we are designing the structures is that how can we ensure that in the aftermath, or we can say at a time of a strong we can say winds that are hitting on the outside, how can we ensure that internal partition walls are also intact, or they may also not get damaged in the case of high winds? Because when we're dealing with the internal pressure, it is not that internal pressure is valid only for a system as a whole. It is although valid a system as a whole, but its effect is applicable for the partition walls also, for the a very for the partition wall just next to the external wall also, for the internal partition walls also. So for that clause 5.3.3 of AS 1170 part 2 help us and explain this particular behavior. So internal walls and ceiling that enclose a space adjacent to external wall, this particular area, and provide an effective seal between the spaces within buildings, because this is the wall that is basically sealing the internal area. So that shall be subjected to pressure derived from space adjacent to the external wall, that is this particular wall. And the likely we can say openings in the external wall in combination with the pressure coefficients shall be taken into account to give the largest magnitude pressure difference across the wall. So we can say that the space adjacent to the external wall, this is also very important, and this is the wall that is basically the ceiling, that's basically sealing the inside from the outside effect. Now net pressure coefficient, if we're talking about these particular internal we can say walls, we do need to refer to we need to take it as 0.4. so 0.4 shall be the net pressure coefficient. We're not talking about the external, we're not talking about the internal, we're talking about the net pressure coefficient for which we do need to design this wall, and this is value is basically 0. Now the second question comes. The second question here is that although we have already designed this particular steel we can say roofing on the top, but at the same time we are also fixing the false ceiling here. Let us say this is the false ceiling which we know we are hanging from this particular arrangement, or there may be services also like plumbing, firefighting, etc. hanging from the ceiling. So there must be some internal pressure effective we can say internal pressure acting on this particular false ceiling also. So this ceiling shall be having a net pressure coefficient. Net pressure coefficient, we're not talking about external or internal, we're talking about net pressure coefficient value as 0.4 can be taken for this particular ceiling arrangement. Now in addition, you need to understand that these ceilings may be exposed to wind induced pressures also, because let us say there is this a flying object came and it may puncture the sheeting here. So there may be we can say a opening here. So because of this opening, the ceiling may face external pressures also at a time of roof leakage, and there may be a potential of large external openings also which may may cause a harm to this particular false ceiling arrangement. So this is the concept that we do need to understand, that the code is also guiding us that how we can take the net pressure coefficients for the internal walls also, for the false ceiling arrangement also, or we can say simply the ceiling arrangement. Now in the earlier lecture we have already discussed about this particular building or this particular hanger structure. So I had already said that I shall discuss in detail about this particular case also. So for that the code is saying us about the clause 5.3.4, where the walls are only on the three sides and there's this large opening on this particular side on one face. So for that, as I said, that we can simply refer to the clause 5.3.4 of the code, and it is saying that when the largest opening in a building is on a wall and the open area, this particular open area, that is basically greater than the sum of the total open area on the roof and the other wall surfaces by a factor of 6 or more, then we can say that we do need to count the open area by volume factor kV. Open area by volume factor, and that is known as the kV. Now kV is basically the code is simply again giving us a guideline that kV can be equal to three values. First value is that kV is equal to 1.01 plus 0.15 log base 10 100 a to the power 3 by 2 divided by volume. For 0.09 less than or equal to 100 into a into 3 by 2 divided by volume, and less than or equal to 3. So if this particular value, that is 100 a to the power 3 by 2 divided by volume, is in between 0.09 and 3, then this equation shall govern, or kV is equal to 0.85 for 100 a to the power 3 by 2 divided by we can say volume less than 0.09, and kV is equal to 1.085 for 100 a to the power 3 by 2 divided by volume. This value is greater than 3. So it is either equal to this or equal to this or equal to this, but depending upon the value of we can say 100 A to the power 3 by 2 divided by volume. So let us say in an equation, we assume that, let us suppose our this value, that is 108 to the power 3 by 2 divided by volume, that is coming equal to 2. So if this is equal to 2, then we do need to refer to this particular equation. So kV is equal to 1.01 plus 0.15 and log base 10 to the power 2. So this is the equation that we do need to simply solve. So simply we can find out the value of log base 10 to. So this value comes out to be 0.3, and that can be multiplied with 0.15, and that needs to be added to plus 1.01. So this value comes out to be 1.055. So we can say that the maximum value of kV, if we enter this 180 to the power 3 by 2 value as 3, then this value comes out to be 1.085. But in our case, as this value was basically equal to 2, so in our case kV value comes out to be 1.055. And if you might be having a confusion, A is basically open area on the wall, divided, and volume is basically the internal volume, that is the total internal volume of the building. So if still we are not able to find out all of these things, then simply we can say that kV is equal to 1 for all other cases. So that is the basic concept of the open area by volume factor kV. Now in the next lecture we shall discuss in detail about the external pressure coefficient.